we've defined our reflection transmission coefficient. We looked at this picture that really everything is based on. No, not this one, where you have this device region. Somewhat arbitrarily define your device region, your left lead, your right lead. And it's this scattering picture of transport where you inject a plane wave into a region where the potential is varying, and so you'll get reflection and transmission. The transmitted part of the wave gives you your transmission coefficient, which is defined as the transmitted flux. This is a fundamental definition, which we'll come back to when we come up with a green function expression for this. The transmitted flux divided by the incident flux, which the way we've set things up is just this transmission amplitude squared times the ratio of the incident and final velocities. And it's got to be the same whether you inject from the left or the right side. Otherwise, you'd violate things like detailed balance, time reversal symmetry, and you'd have current flowing in equilibrium. Okay, now we're going to move to the picture that we're going to use for the rest of the course, which is a tight binding picture, which is the one you just became very familiar with in 208, which is why 208 is a prerequisite for this course. So before I just drew sort of a box for our device, now our device is going to be a set of lattice points or a set of states, and we'll initially use just our simple 1D tight binding model. And so, let's see. And so that we can actually write down explicit matrices that represent our device Hamiltonian and our green function. My device is going to be exactly 3 lattice sites. So our device Hamiltonian eventually will just be a 3x3 matrix, something that you can just write down and look at and understand everything about it. And so these dashed lines represent the boundary between the device and the left and right leads. So over here I've got the right lead. Over here I have the left lead. In the middle, of course, I have my device. And for, a while, we're just going to have one basis state on each site. So I'll just represent that by, you can just think of it as a little s orbital. On each lattice site. And so they'll all have the same site energy, epsilon. And they all have our hopping nearest neighbor, hopping matrix element. So it's our usual nearest neighbor, single band, tight binding model. And so what we want to do is take, what we just did in the continuum representation and formulate it in this tight binding model. There's your lattice constant A. Typical one-band tight binding model. Okay. Um, so, you know, let's see if I can back up. I know it's been a couple of weeks. So we're going to represent our wave, our arbitrary wave function as we do in any tight binding model. Right, some linear combination of our localized orbitals with some complex amplitude c, right? And then we're going to act on that with our Hamiltonian, look at H. There's our Schrodinger equation. And so I write out, I put in this sum for psi. I'm going to have H acting on this sum over N, Sn, Cn. It's going to equal E and sum M. Okay, I just wrote out psi in terms of the sum of the basis over the basis states. And then to turn this into our matrix equation, we hit it from the left-hand side with S. I used N and M already. S T, I guess. Right, we hit the whole thing on from the left-hand side with this bra, S sub P. A little more room here. Okay, so on the left-hand side, you know, E is just a constant, so SP is going to collapse that sum. So the left-hand side just becomes, and we assume an orthonormal basis, right? So the left-hand side just becomes E C sub P, right? All happy with that? No arguments there? You happy with the right-hand side? Yes? 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 So E is just a number. So this, you know, I can move the number. E is just some number over here. That doesn't matter, right? And so I can move this S sub P inside the sum, and so inside the sum I have SP Sm. And this is an orthonormal basis, so this is just delta, Kronecker delta M, comma P, which collapses the sum. It's only non-zero when M equals P, which just gives me C sub P. All right? Okay. And then on the left-hand side, what have I got? Well, I've got just the matrix elements of H. I mean, this, I'll pull my sum out here, sum over N. This is what we mean by a matrix element of H. So this is just H P comma N C sub N. Right? And this is my matrix equation for the amplitudes. Right? Where H is H P comma N is just SP H Sn. And so that's, I mean, always how we convert the Schrodinger's equation into a matrix equation that you could stick into Matlab. Okay, now this is our tight binding, our nearest neighbor tight binding model. So we know exactly if we choose a row. So let's see. So what do we want to do? So this matrix equation we have down here, that we've written down, and it's just an eigenvalue equation in matrix form. The problem is this matrix is infinite, because these sites really go from like negative infinity to infinity. And so putting infinite matrices into Matlab is a problem. So we have to find some way to deal with making it tractable. Okay, this is an infinite, this matrix, if you remember the form in your tight binding model, this matrix is an infinite tridiagonal matrix. It has the diagonal terms, the epsilons, and the off-diagonal terms, coupling to the nearest neighbor. So if we looked at any row, let's look at row 1 of this equation. Row 1 of this eigenvalue equation would be T C0 plus epsilon minus E C1 plus T C2 equals 0. I just move the E on the right-hand side over onto the left-hand side. Right, this is here's the full matrix equation down here at the bottom. And so the diagonal term C sub P I just moved to the left-hand side here. So this is what the equation for row 1 would look like, and the equation for every row, as long as there's no bias applied or anything, looks exactly the same. If I'm just thinking, let's just start with an infinite uniform chain of sites. So there's no difference between the leads and the device initially. Right? Every row, when we started off, this is where we started in 208, looks just like this row. Right? Everything just gets shifted over by one site. Yeah.
Why the matrix is infinite?
Because
This is periodic structure, right?
yeah, and like any crystal, you let the sites go from whatever your counting system, say 1 to n, and you let n go to infinity. Right? You take this what they call thermodynamic limit, where how does this work? You let the number of sites go to infinity.
Eventually, I have to choose n infinite.
Right. I mean, it's periodic, but at the end of the day, we always let n basically go to, because when we convert the sums to integrals, we have this 2 pi over L, but that's really an infinitesimal. 2 pi. This is the spacing between k vectors in k space. And we consider k to be a continuum in the Brillouin zone. And the distance between each k is 2 pi over L. And if the distance is going to 0, it means L has gone to infinity. Right? We do not have when we're doing an ideal crystal, we do not have a discrete spectrum in k space. It's just continuous if you plot those EK relationships. So, in this limit that we always take of our system, you have an infinite matrix. And I mean, you can also think, well, there's more profound reasons why we really need to do this when we're doing transport. If you really have periodic boundary conditions and try to do transport, you probably won't. It'd be really hard to apply bias because it has to be periodic. hard to have the drain at a different voltage than the source. There'd be conceptual difficulties, right? It can no longer be periodic if you've applied a bias. And so, for these reasons, especially when we do
The potential at one end will be lower than the
Yeah,
other
right.
because we have been biased.
Yeah, yeah,
So
yeah.
it can be-
Yeah. So you've broken the periodicity. Okay. So this is what every row looks like, as long as there's no potential variation. And in the leads, we assume the leads are just ideal regions of the crystal where there's no potential variation. So the crucial point is that our objective is to solve for the amplitudes C1, C2, and C3. This is why I made my device only 3 sites long, so we could be very specific and not get confused here. Solve for the amplitude C1, C2, and 3 of the quote device. Because it's only in the device that something interesting has happened, that you're going to have a potential variation. You need, if you're doing a full Schrodinger-Poisson equation, you need these amplitudes because they're going to give you the charge density in the device. And you would feed that charge density back into Poisson's equation, say, get yourself a new potential and iterate until convergence. So we need these amplitudes to get both the charge density and the current. And this is what we want to solve. So really, if we have this, we have everything we need. So out of these infinite number of C's, C negative infinity to C plus infinity, we only need C1 through 3. So the whole problem is how to get C1 through 3 when your matrix is actually infinite. Okay. And, I've written this for row 1, and what you see here is that, all we really need is this guy and this guy. Unfortunately, so these guys are in the device, right? Unfortunately, the device couples to the left lead. And then if I wrote the same equation for C0, C0 would couple to C minus 1, et cetera, back to negative infinity. So everything is coupled together. Similarly, if I wrote the equation for row, what would that be? 3, row 3 would couple, I would just move each one of these indices by 2. So then I would have a C1, a C, what would I have? By 2. So C2, that's supposed to be a 2. This would become a 2. This would become a 3. This would become a 4. So if I wrote it for row 2, you would see that, all I need is C2 and C3, but these couple to C4 in the right lead. So and C4 couples to C5, etc. So I got to figure out a way to solve for C1 through C3 and somehow do something about these infinite leads on either side. Okay? And that's the whole trick. That's what this is really all about for coherent transport. After you understand this, the rest is sort of numerical details. Okay. But we do have some information about these leads. We know they're sort of ideal leads. We know that the eigenstates are eigenstates of the unperturbed Hamiltonian out in the leads. And so we know the general form of the eigenstates of the, this injected wave and injected and reflected and transmitted waves in the leads. So let's write the general form for this injected and reflected wave in the left lead in our tight binding representation. So we're going to just redo everything now in our tight binding representation. So this is the left so the state in the left lead psi sub L so I've got my injected part, e to the I k sub L, lattice constant, n minus 1. So the lattice constant times the integer gives me the position. So when I'm at site 1, the phase is 0, is the way we're setting this up. When I'm at site 1, which is the first node of quote the device, the phase is 0. And I have the reflected component, RL, e to the, I'm going to I, K, L, A times, I'm just changing the sign up here, 1 minus n. Okay. So this is what it looks like, what I wrote down the injected and reflected plane waves in the continuum representation. This is what they look like in our tight binding basis. Okay. Everyone happy with that? It just looked like it, right? Before we had the psi L in our continuum representation. I'll put a C for continuum. We just wrote down e to the I, k left, x minus x sub L, plus the reflected r sub r, e to the minus I, k, L, x minus x sub L. Right, so that was in the continuum form, and up above is just a discrete lattice form. Where x becomes a times n, or n minus 1. We're just choosing the phase to be 0 at site 1. All right? All seem reasonable? Going from the continuum to the lattice. Okay, now, if we look at this the lattice form, the first equation, you know, the general form was just a sum of S sub n times C sub n, and looking at the equation, the top equation, this means that the form for the complex amplitudes in the leads, well, we know that C sub n in the lead is equal to all this stuff multiplying S sub n in the upper equation. So that's just e to the I, k, L, A, n minus 1, plus r sub L, e to the I, k, L, A, 1 minus n. Again, I just want to emphasize, so this is our, this sum just tells you where this is, what states is, for all states less than or equal to, all sites less than or equal to site 1. So it's our left lead state.
If it is lead, then why are you including 1?
You are the first person to ask that. Wow. Maybe forever. Usually this is something I try to sweep under the rug and no one ever asks. Well, can we just go with this for a while? Okay. Um, yeah. You know, in this representation, in the continuum representation, you know, the where exactly, you know, you're in the limit, infinitesimal limit, so this boundary between the lead and the device is really at a specific point. But you know, in this representation, the boundary is kind of like somewhere between 0 and 1, right? And we'll see when we set it up in this deriving it from a wave function approach. We need to include site 1 like this. And I think what it really means is that site 1 can be part of your device, but the potential in site 1, when we derive it like this is why I try to sweep it under the rug because it's so confusing. When we derive it from the Schrodinger equation, the potential at site 1 has to be the same as the potential in the whole left lead for all this to really formally hold through. When we do it in Negev, that's not the case. Site 1 can be different. And yet the equations come out to be identical. So for now, don't worry about site 1 and site 3 when I include them in the definitions of my lead wave functions. Let's just go with this. We can come back to this after we redo everything with Negev and the recursive Green function algorithm. You'll see that it really doesn't matter. Anyhow, all right. I've been waiting for someone to ask for a couple of years now. So where are we? We are here. So this is the general form of the amplitude for our wave function being injected from, it's the amplitude for our left injected scattering state in the left lead is what it is. So since now we're going to look at what we want to do is use this information, use this known form for the C in the lead to try to do something to somehow write C0 in terms of C1. If we can write C0 in terms of C1, then we've basically separated out. You know, we can write a closed form equation for just C1, C2, and C3, provided we do the same thing for the right-hand lead also. So our goal is to write C0 in terms of C1, and then we'll have a closed set of equations just using C1 through C3. So that's our goal. And we're going to use this known form of the C sub n's in the lead to do that. So that's our approach. Okay, so using this known form for Cn for our left lead, then, well, just, you know, putting in values for n, I have C0 is equal to e to the minus I KLA plus R sub L e to the I KLA. That's my C0. Similarly, C1 is equal to 1 plus R sub L, because we defined everything so that at site 1 the phase is 0, or the phase factor is 1. Okay, so that's what I have for C0 and C1. That's nice. Problem is that RL is not known. So far I've got like 3 unknowns and 2 equations, right? I got C0, C1, and R sub L. KL is known. I mean, K, you just choose a K to inject from. So that's the unknowns are C0, C1, and R sub L. But let's multiply the equation for C1 by e to the I k a. Copy these onto the next page. Okay, so now we're going to multiply the equation for C1 by e to the I k a. So we have e to the I k l a C1 is equal to e to the I k l a plus r sub l e to the I k l a. And now we subtract. It looks like if we subtract, we can get rid of RL and just have an equation for C0 and C1, which is what we need. We want to write C0 in terms of C1. So if I subtract the bottom equation from the top equation, I'm going to have C0 minus e to the I k l a C1 is equal to e to the minus minus e to the plus. Right, that's what I get if I subtract the lower equation from the top equation. I've gotten rid of the RL. I just have an equation relating C0 to C1. And so C0 is equal to C1 plus minus I KLA minus KLA. So now I've solved for C0 in terms of C1, and I can do the same thing with the right-hand side, solve for C4 in terms of C3, going through the same procedure, and now I will have a closed form set of equations for C1 through C3, basically a 3x3 set of matrix equations. So what we want to do now is take this expression for C0 and put it back into our original equation for row 1 here, because this is where it couples to C1, so we need to substitute it back into here and see what the equation for row 1 comes out to be. So that's what we're going to do. Okay, we're going to substitute it into that value for C0 there and get a new equation for row 1 of our matrix. It's purely in terms of C1 and C2. Now it will no longer have a C0 in it. So if I do that, row 1 will become T e to the I KLA C1, and I had a T C0 plus T times the other two terms, e to the minus I KLA minus e to the I KLA. So this is what I get from substituting in for C0 into that equation for row 1. And then the other two terms are still there, plus epsilon minus E, C1 plus T, C2 equals 0. So this is my new equation for row 1 of the matrix, which is no longer coupled to C0. Okay, it seems like a little bit of sleight of hand, but we took this known form for the left injected wave function, and we used it to solve for C0 in terms of C1, and then we put that back into row 1 of the matrix equation, and we get an equation for C1 and C2 alone. Let me rewrite it and put, so now, what you notice is that now we have, before it was a homogeneous equations for the C's, and now we have an inhomogeneous term there. It's not, it's an inhomogeneous term, it's not multiplying any C, and so we're going to put that on the right-hand side. We've got this new term we didn't have before. It's inhomogeneous. It's not multiplying any C, any amplitude. And so that we're going to stick on the right-hand side, and that becomes a source term. So putting that on the right-hand side, we have, and rearranging a few things, we have E minus epsilon minus T E to the I K L A C1 minus T C2 is equal to T times E to the minus I K L A minus E to the I K L A. Yeah, I just combined all the terms, the C1 terms, and I moved the inhomogeneous term over to the right-hand side. So this is what the equation for row 1 of that infinite Hamiltonian becomes. It's now decoupled from the left lead. Now let's look at the inhomogeneous, this new term on the right-hand side, this new inhomogeneous term. So this guy over here is this term becomes negative I 2t sine Ka, right? I just combined the two exponentials into a sine function, right, using the definition of e to the I Ka minus e to the minus I Ka is 2I sine Ka. That's all I used. Okay. In case everyone is really slow after the break, e to the I theta minus e to the minus I theta is 2I sine theta. That's all I used. All right. Okay, well, big whoop. Yep, that's what it is. But now let's look at our tight binding dispersion. So our E versus K relation. We spent so much time on last quarter. In the tight binding 1D model, we know that E is equal to epsilon plus 2t cosine Ka. Right? And this is a tight binding model we're using. This is a Hamiltonian of our leads, so this is true in the leads. And the velocity, v, which is defined as 1 over h bar dE dk, is just, well, just take the derivative, that's negative 2ta over h bar sine Ka. And so we're just going to take this definition for the velocity and substitute it into here. K sub L, so this is K sub L for the left-hand side. And write this term on the right-hand side in terms of the injection velocity. Okay? So doing that, my equation for rho 1, still working on rho 1 here. My equation for rho 1 becomes E minus epsilon okay, since I defined t's the way I defined it, t's were negative, so I'm going to explicitly make the sign explicit here. T e to the I K L A C1 minus T C2 is equal to I H bar injection velocity over A. Just substituting in our definition for velocity for what we had on the right-hand side before. So this V sub L is the velocity of the injected state with that wave number K sub L in the left lead. And the way I wrote the Hamiltonian, T is less than 0. So I wanted to make the sign of this term here explicit. That'll become important later on. I use the absolute magnitude to make it clear that I have something positive there. Okay. So we've taken care of the left-hand lead here, and we've set up the situation where everything we've done so far, we assume we're injecting from the left. And so if you inject from the left, you have your injected wave, your reflected wave. On the right-hand side, we just have a transmitted wave. What comes out, there's nothing that's going to cause any reflection when you come out the right. So the form of our scattering wave function on the right-hand side is going to be different. So let's go through the right-hand side and see what happens on the right-hand side. So in the right lead, so we're injecting from, just to keep track of what we're doing, we're injecting from the left lead. And so let's look at the right lead. And And what's coming out of the right lead is what's been transmitted through the device. So in the right lead, the form of the wave function is equal to sum n greater than or equal to 3, because of my 3-node device, S sub n so I get T sub R e to the I K sub R A n minus 3. So that would be the form of the wave function coming out the right-hand side. And so, again, we go through the same procedure. The values for C3 and C4, because we got to write C4 in terms of C3, just to truncate our infinite set of equations. We have C3 is this transmitted amplitude. C4 is TR e to the I KRA. And so this is actually pretty easy, which means, compared to the left lead, which means that C4 is equal to e to the I KR A C3. Right? We don't have to do very much here. And so the equation for the for row 3 which couples to C4 is T C2 plus epsilon minus E C3 plus T C4 equals 0. So I need to substitute this in for C4 there. That's my initial equation for the third row, which couples to the right lead. So I'm just going to substitute in this e to the I KRA C3 for C4, and I get a truncated equation for the third row of the matrix. So I'm going to get TC2 plus, I'm going to multiply through by -1, plus E minus epsilon plus magnitude T e to the I KRA C3 equals 0. So there's no, for the third row, there's no inhomogeneous term. And I only got an inhomogeneous term on the first row that couples to the lead where you're injecting from. And so now if we write out the so the center three by three device part of the eigenvalue equation is now this. So minus epsilon plus magnitude of t e to the I k left a minus t 0 minus t e minus epsilon minus t and 0 minus t e minus epsilon plus magnitude t e to the I k l a So this is what the 3 by 3 matrix becomes. Let me see if I can shrink it. Okay, here's my 3 by 3 matrix, and it's acting on C1, C2, and C3 are multiplying. C1, C2, and C3, and that's equal to, on the right-hand side, we had that one inhomogeneous term in row 1, and that's I h bar velocity over A. That's what that eigenvalue equation becomes. When we kind of use algebra to, physicists would call it integrate out the leads. And we solve for C0 in terms of C1, solve for C4 in terms of C3. Assuming that we were injecting from the left contact, and what you end up with, this eigenvalue equation, which we started off with just HC equals EC, a homogeneous eigenvalue equation, becomes this equation with an inhomogeneous source term on the right-hand side. And if we inject from the left, if we inject, so here we're injecting from the right contact. If we inject from the left contact, let's see if I can get my same. If we go through the same exercise and inject from the right contact, we will get the exact same 3 by 3 matrix, which people call the device Hamiltonian. Multiplying the vector C1, C2, C3. The only difference is now we're injecting from the right, so the inhomogeneous term is going to show up in row 3 that couples to the right contact. So the only difference is where the inhomogeneous term is and the velocity that goes into it, because the velocity that you inject from the right under bias, for example, at the same energy would be different in the drain compared to the source, because it'd be at a higher kinetic energy. Okay. Okay, so let's look at the right-hand side. Sorry. Let's look at the right-hand side. Try to give some physical insight. V is the velocity of your injected wave. So you can view V over A as an attempt rate. As an attempt rate, the units are going to be 1 over time. Right? And so this source term can be viewed as just h bar times an attempt rate. So by the source term, I mean this term on the right-hand side of the equation can be just viewed as h bar times your attempt rate, 1 over tau. H bar, why am I spelling this out? Idiot. H bar times an attempt rate. So, let's see. This tau is the time that an injected wave spends at a given site n. Right? It's moving along with velocity v. The length associated with each site is a. So v divided by a is the average time it spends at any site n. Right? Velocity divided by the length. So if we multiply this rate times h bar divided by tau, the units of that are energy. So that gives an energy that corresponds to this lifetime. So h bar over tau is an energy corresponding to this lifetime that the electron spends on any given site n being injected from the left lead. So h bar over tau is the energy corresponding to this average lifetime V over A, that it spends the time it spends on any given site. And so the standard notation for a lifetime, an energy that's related to a lifetime, standard notation for an energy that represents a lifetime is gamma. So whatever lifetime you're interested in, the standard notation people use, whether it could be a scattering lifetime, the lifetime you're spending on a site, your resonant lifetime, the energy associated with that lifetime is always h bar divided by the lifetime is gamma. That's the sort of the general symbol people use to denote an energy that represents a lifetime, a finite lifetime. So you could have a resonant lifetime that you can think of as a Q factor. The energy associated with that, for you electrical engineers, the frequency width associated with that would be gamma. And so we're going to write this non-zero term on the right-hand side in terms of gamma. So the right-hand side of our equation is going to become I gamma L, or I gamma R, where gamma L is h bar left velocity over A, and gamma R is h bar right velocity over A. And that's how we're going to write those now on those right-hand side source terms. And now let's look at this matrix, the final form of our 3x3 matrix. So the middle row is unchanged. The middle row is exactly what we would have had, because the middle row didn't couple to either the left or the right contacts. It was solely contained within a device. So before we started manipulating this, every row looked like the middle row. They were just shifted over to the right or to the left as we went up and down the diagonal. Right? You had this infinite tridiagonal matrix. But now after our manipulation and, quote, integrating out the leads, as the physicists call it, we have what's changed are the two corner, the upper corner and lower corner diagonal blocks is what has changed in this matrix. Right? In this 3x3 part of the matrix, what has changed are these two upper left and lower right diagonal blocks. And the thing that's changed, well, the E minus epsilon is still there. That was there from before. But now we have this new term, this magnitude of T e to the IKA. That's a new term that's appeared on the corner blocks of this 3x3 section of the Hamiltonian. So now, let's take a look at this new term, this term here. Right, this is what's new. Out of all of this derivation we've done so far, this is the new stuff. These are the things that are new. Okay, these two corner blocks of the, quote, Hamiltonian have been modified. And we ended up with these inhomogeneous terms on the right-hand side, okay? And of course, now we've kind of thrown away the whole rest of this infinite matrix. All we have to do now, we have this closed set of equations to solve for C1, C2, and C3. And the effect of the leads has completely been taken into account through these new terms that we've picked up in our equations, these two corner terms in the matrix and the inhomogeneous term on the right-hand side. So we just looked at the inhomogeneous term on the right-hand side. Now let's look at these new corner terms in the matrix. So understand what they represent physically. Let's write them out as T e to the IKA is equal to T cosine Ka plus IT And everything really should have a subscript, say L if you're dealing with the upper block, or R if you're dealing with the lower block. I'm just suppressing the subscript. Okay, I'll put it in the first set of equations. So L, it should be L, 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 L. So that's where the subscripts go, and from now on I'm not going to worry about them. Unless, okay. So let's look at the imaginary part of this term. The imaginary component. And the imaginary part is equal to H bar VL over 2A, which is H bar over 2 tau, which is just, to be clear, gamma L over 2. That's what the imaginary part is equal to. Same gamma L that's coming out of your inhomogeneous term on the right-hand side. So these corner terms, where did I write them? So these corner terms, so here's the one for the left, here's a similar one for that lower right corner. These corner terms that get added onto the diagonal block, these are what are called your self-energies that represent the effect of those semi-infinite contacts. So these extra corner terms in the upper right, lower left corner, your matrix, are called self-energies. And the symbol always used for them is an uppercase sigma. And in this case, there's a specific self-energy. This R stands for retarded, not because it's stupid, but because it comes from a causal self-energy. We won't really get into that for a while. It doesn't stand for right or left. It's a retarded self-energy. And so the general form for that corner block is E minus epsilon minus sigma R. And so just by making the identification, sigma R left is equal to, at least in this simple single band 1D tight binding model, negative T e to the I KLA, which is equal to T cosine KA minus I gamma L over 2. And similarly for the bottom right corner, due to coupling to the right-hand lead, and the imaginary part of the sigmas is related to the injection rates from your left or right lead. So gamma L is equal to -2 imaginary sigma R to the left lane. And gamma right is -2 imaginary sigma R due to the right lead. And these turn out to be very general relationships between the sigma that goes into the matrix and the gamma due to injection from your lead, or if you were thinking of something else, from phonons or whatever. But for now, we're just thinking about a left lead and a right lead. So now that we've done this, it's time to think about what all this means physically, what's happened to our Hamiltonian equation. If you go back and look at this form of the equation that we derived, what we call our Hamiltonian has been modified. This matrix has been modified. And the modification can be represented like this. So we have a new Hamiltonian for our device region, which is just a 3x3 part, a 3x3 matrix, which is the original Hamiltonian, plus this extra term, which represents the coupling to the semi-infinite leads, which takes into account everything to the left and everything to the right. The next thing to notice is that our effective Hamiltonian is not Hermitian. And the reason is our self-energies have an imaginary part to them. And these self-energies go on the diagonal. And there's no way H dagger can equal H if you have imaginary terms on the diagonal, because the diagonals will switch sign when you dagger H, right? When you dagger H, you take the transpose complex conjugate. So the diagonals stay where they are when you take the transpose, but if you take the complex conjugate, if you have an imaginary term in the diagonal, it's going to change sign. And so there's no way any matrix with imaginary terms in the diagonal can be Hermitian. So this effective Hamiltonian, HD minus sigma, is no longer Hermitian. And this is probably the first time you've dealt with some effective Hamiltonian that's not Hermitian. And so, you may bump into this in your quantum courses where they say, well, if you have an imaginary potential, you're going to lose flux. As time progresses, flux will just disappear from your system. Flux is no longer conserved. But now this 3x3 Hamiltonian represents a finite system. And so if I put an electron in site 2, after some time, it's no longer going to be found in site 1, 2, or 3. It's going to be somewhere in those semi-infinite leads. And so these imaginary terms represent that loss from your finite system into your semi-infinite reservoirs, these leads on either side. These represent the lifetime of, if you put an electron in that device, how long will it stay in those, either node 1, 2, or 3 before it leaks out into the leads. That's what this finite lifetime, it has a physical meaning, and that's what it means. Because we truncated the system down to something finite, there's now a region where if the electron moves into another region, it's no longer in our domain and it's been lost. So electrons in the domain do have a finite lifetime. They can be lost. They can come in, from a lead, and they can go, and that represents either a gain or loss of electrons to the system. And so that's what these imaginary terms are taking into account in the corners, and they only show up on the corners because that's where you couple to the leads. So if an electron moves to the corner, there's a finite lifetime. It represents leaking out into the left or right lead. I have 459. So I think we'll just stop there. Pick up next time. And we'll think about that. As usual, I'll post videos and notes. Get the most current version of these typed up notes up onto iLearn. We just started off with Schrodinger's equation and did some algebra. We pulled out these famous self-energies that you run into with negative and the gammas. We'll review all this next time.